You know, it's funny. We drive past them every single day. Utility poles, lines crisscrossing everywhere. You barely even notice them, right? But when you stop and think, there's this incredible amount of engineering and safety hidden in plain sight. So today, that's what we're doing. A deep dive into that world, the really detailed rules that govern how all this utility infrastructure gets built. We're going to focus specifically on the conductors, the wires, and the insulators that keep everything safe. Our mission really is to unpack some of the standards, like those from the California Public Utilities Commission on conductors and insulators, just to see what keeps our power and communications, humming along safely.
And it's worth stressing, these aren't just random suggestions. These rules have been built up, refined over decades. They're all about public safety first and foremost, and making sure these systems last. Every single spec, every material choice, it's there to handle real-world conditions and prevent failures.
Okay, let's get into it then. Starting right at the heart, the conductors, the wires themselves. What are they actually made of? Why these specific materials?
Right. Well, the standards, if you look at something like Rule 49.4a, they're quite specific. You've got your traditional materials like copper, of course, also copper-covered steel, bronze, even composites using those. But then there's also aluminum, and often you'll see ACSR, that's aluminum cable steel reinforced.
Ah, the steel core adds strength.
Exactly. And galvanized iron or steel, too, the common thread, they all have to be corrosion resisting. And that phrase, corrosion resisting, it's absolutely critical, not just a minor detail.
Why so critical? Just longevity.
Longevity, yes, but primarily safety. Think about it. A corroded wire is a weak wire. Imagine that snapping in high winds. You could have a live high-voltage line falling. So preventing rust and deterioration is fundamental.
That makes total sense. Okay, so materials are key. Now, what about size? This is where I hear it gets really interesting. It's not just bigger is better.
No, not at all. There's real science to it. Rule 49.4b and its associated Table 8, they give guidance on minimum sizes, especially for typical spans, say, 150 feet or less.
Table 8, so it's like a chart.
Yeah, think of it like a decision matrix. It lays out minimum sizes based on a couple of key factors. First is loading conditions, heavy or light. Heavy loading considers things like ice buildup, high winds, stuff that adds significant weight and stress.
Okay.
Then there's the grade of construction, grades like A, B, C, or F. This reflects how critical the line is. Grade A might be a major transmission line, highest safety factors needed. Grade C could be, say, a local distribution line in a less dense area. Different risks, different requirements.
So give me an example. How would that table look?
Okay, so let's say you're in a heavy loading district, maybe somewhere with icy winters.
Yeah.
For a critical grade A line, if you're using soft copper, the table might specify a minimum of, say, hashtag 480G. That's American wire gauge. A smaller number means thicker wire.
Got it.
But if you were using that ACSR, the aluminum with the steel core, maybe it's a hashtag 1 AWG minimum. It's lighter, but the steel gives it strength. So the size requirement changes based on the material's properties under load.
So the table directly connects the environment, the line's importance, and the material to a minimum size.
Precisely. It shows how engineers have to balance all those factors.
And these are just minimums, you said, so sometimes they need to go bigger anyway.
Oh, definitely. These are the absolute floor. Very often, engineers need to use larger conductors. Why? Well, to maintain proper sag, you don't want wires dipping too low.
Right.
Also, to meet overall safety factors, ensuring the wire can handle unexpected loads, and crucially, to maintain clearances, enough space above ground and enough space between different wires.
Clearances, yeah, that seems vital.
Absolutely. And the rules also mention specific exceptions, like maybe different rules apply if communication line crosses a major railway. And there's another interesting wrinkle. Sometimes pure tensile strength can substitute for just meeting a minimum size, especially on lower voltage lines.
Ah, okay. So it's not just thickness. It's about the pull it can handle. Let's talk about that strength. What does that mean here?
Yeah, that takes us to Rule 49.4c, all about strength, and specifically tensile strength. Think of it like how much force can you apply pulling on that wire before it breaks. It's a fundamental measure of its integrity.
And critical for safety, I imagine.
Hugely. So the rules set minimum tensile strengths based on loading and grade. For example, heavy loading, grade A construction, spans over 150 feet. The conductor needs the strength of at least a hashtag 4 AWG medium R-drawn copper wire. That's a specific benchmark.
Okay.
In light loading areas for the same grade A, but maybe slightly longer span, say 150 to 300 feet, it might drop slightly to the strength of hashtag 6 AWG medium hard copper.
So it varies. What about the lines coming to our houses? Lower voltage stuff.
Right. For supply conductors under 750 volts, typical residential stuff in grade B or C spans under 150 feet. The requirement might be the strength of an ACTAG 8 AWG soft-drawn copper wire. Still strong, but scaled to the application.
It's all very specific. Is there one safety rule related to strength that really stands out, thinking about worst-case scenarios?
Yes, there definitely is. Rule 49.4C4. This is a big one. It deals with high voltage lines, say over 17,000 volts, that cross over lower voltage lines or even cross over a public road.
Right, a really hazardous situation if something breaks.
Exactly. So those high voltage conductors must have a tensile strength at least equal to that hashtag 4 AWG stranded medium hard-drawn copper benchmark. Or, and this is key, the poles themselves have to be placed strategically, so that even if the high voltage wire does break, it physically cannot fall onto the lower lines or land within 10 feet of the road surface.
Wow, so it's designing for failure, in a way.
It's designing to prevent catastrophic failure, yes. It's asking, if the worst happens, how do we contain the danger? Really important foresight.
Incredible. Okay, and what about sags and tensions? You mentioned sag. You can't just string these wires super tight, can you?
No, absolutely not. That's another danger. While strength is key, overtensioning is bad. Rule 49.4C5 is clear. Under the specified loading conditions, again, considering ice, wind the tension put on a conductor can't exceed half of its ultimate breaking strength.
Half, so a big safety margin.
A 50% safety margin, yes. If a wire could theoretically break at 4,000 pounds of tension, the maximal working tension allowed might only be 2,000 pounds. It balances keeping the wire taut enough to manage sag, but without putting excessive constant stress on it or its supports.
And I see a note here about service drops. What are those exactly? Different rules.
Service drops, those are the wires that run from the main pole on the street directly to a building, like your house.
Ah, the final connection.
Right, and they have their own specs. For instance, supply service drops, the ones carrying power up to 750 volts, they usually need a weather-resistant covering, extra protection. And even communication service drops, like for phone or internet, have strength rules. A typical paired wire, maybe hashtag 18 AWG high-strength bronze, might need a minimum breaking strength of, say, 340 pounds.
340 pounds for a thin communication wire.
Sounds like a lot, right? But it ensures it can withstand wind, maybe tree branches, things like that. It highlights how even the smaller components are engineered for resilience.
It all seems to weave together. Which brings us to something like Rule 49.4E, which just says, all electrical connections shall be of suitable electrical and mechanical design. Simple phrase, but sounds important.
Absolutely. It ties everything together. A connection point where wires join or connect to equipment is often a potential weak spot. This rule basically says that connections have to be just as good electrically and mechanically as the wire itself. It needs to conduct properly and hold strong under stress. No weak links allowed.
Okay, so that covers the conductors, the wires having the heavy lifting. But what about the things keeping them, well, keeping them apart and safe? The insulators.
Yes, the insulator, the unsung heroes you called them earlier. That's a good description. Rule 49.5 covers them. You usually see them as those ceramic or glass, sometimes polymer things on the poles. Their main job is electrical isolation.
Stopping the electricity from going where it shouldn't.
Precisely. Preventing it from flowing into the pole, the support structure, or down a guy wire to the ground. They have to be strong enough mechanically to handle the weight and tension of the wires, again with specific safety factors under different load conditions.
And the rules get specific here too.
Oh, incredibly specific. Here's a detail from 49.5A that shows the level we're talking about. Pin insulators, the common type that sit on top of a pin on the crossarm, they must engage the threads of that pin for at least 2.5 turns.
2.5 turns, that specific.
Yes. It ensures a really secure fit, preventing loosening from vibration or weather over years and years. It's that kind of detail that ensures long-term reliability, and it applies elsewhere too. Guy insulators put into the supporting guy wires, have to be at least as strong mechanically as the guy wire itself. And those bigger post insulators you see on higher voltage lines. They have defined cantilever strengths requirements, tested according to established industry standards. It's all about ensuring that electrical barrier holds up mechanically and electrically.
Wow. Okay, and briefly, supporting all of the structure, the guys and anchors.
Right, the foundation, in a way. Rule 49.6 touches on them. Often partly buried, so maybe less visible. But Rule 49.6a kicks off with a familiar theme.
Hmm.
The exposed surface of all guys and guy rods shall be of corrosion-resisting material.
There's that corrosion resistance again.
It keeps coming up, doesn't it? Because these things are often in contact with soil, moisture. They have to resist degradation to keep the pole stable. Their size and strength are also, you guessed it, determined by the loads they need to support. Meeting required safety factors under those different loading conditions. Everything is interconnected.
It really is. So stepping back from all this technical detail, what really stands out to you? It feels like so much more than just stringing up some wires.
It absolutely is. When you connect it to the bigger picture, you see these aren't just, bureaucratic rules. They form the actual bedrock of our modern electrical and communication grids. It's all about ensuring public safety and keeping the lights on, keeping data flowing. What really strikes me is the sheer level of detail, the foresight involved, and the fact that these are living documents. We mentioned rules referencing standards from 2014, but also going way back to the 60s, even 1951. They get reviewed, updated, based on experience and new technology.
Constant evolution.
Constant evolution. Every single material spec, every minimum size, every strength test, it exists for a very specific reason, usually learned the hard way, perhaps. To prevent failures, manage risk, and maintain the services we all depend on. It's really quite remarkable, the hidden complexity.
It really is. So maybe next time you're driving or even just walking and you glance up at a utility pole, take a second. Consider all that invisible engineering, the material science, the structural calculations, the safety factors, all working together to keep those lines up there, doing their job safely. It's this complex dance governed by these incredibly detailed rules we've just scratched the surface of. Makes you wonder, doesn't it? What other intricate, vital regulations are quietly shaping the safety and reliability of the world all around us, things we probably take completely for granted every single day?